When we perform a chi-square test to assess whether or not differences between our observed and expected values are significantly different, we need to use either a spreadsheet or this chi-square table to find out, based on the chi-square test statistic value, whether that represents an insignificant or a significant difference between the observed and expected values. To use a chi-square table, you need to have two pieces of information: the number of degrees of freedom and your chi-square test statistic value. The number of degrees of freedom are shown here in the column on the left, and we're going to focus on a particular row related to that degree of freedom for your problem. The numbers inside the table itself are the chi-square test statistic values. Those are the values you get from conducting the chi-square formula. When you know your degrees of freedom and the chi-square value, you look up the pair of cells that flanks your chi-square value. So let's assume we're talking about 3 degrees of freedom, and we calculate a chi-square value of 1.5. First, we would focus on the row containing degrees of freedom of 3, and then we would look at where 1.5 occurs in the table. From there, we look up in the header of the table, and this is where the p-values exist. In this case, we see that 1.5 for 3 degrees of freedom lies between p-values of 0.7 and 0.6. What this means is this corresponds to the probability of the null hypothesis being correct of between 60 and 70%. That's pretty good odds in our favor that the null hypothesis, your expectation, is correct or supported by the data. When the p-value is less than 0.05, those are the shaded red numbers here, that is when we suspect that the observed and expected values are significantly different, which means that our expectation or a null hypothesis is incorrect or rejected. Now let's take a look at a specific example and how we use the chi-square table to interpret the results. In this example, let's consider a family where 2 parents have 3 daughters and 0 sons. We might want to know if this constitutes evidence that the father has no Y chromosome. So our null hypothesis or expectation is that the father does have a Y chromosome, in which case he should produce an equal number of sons and daughters. With 2 categories, sons and daughters, we have 1 degree of freedom. And in this case, the chi-square value associated with this test is 3. So, with 1 degree of freedom and a chi-square test statistic value of 3, we can zoom into our table and see that this p-value lies somewhere between 0.05 and 0.1. When we find a p-value is greater than 0.05, that indicates that the observed and the expected values are similar. That is, our expectation or our null hypothesis is supported. In contrast, when a p-value is less than or equal to 0.05, this is information that suggests that our observed and expected values are different. They're not equal. This means that our expectation or our null hypothesis is not supported and is rejected. In this case, then, even though 3 daughters and 0 sons is different from our expectation of 1.5 each, this is not a significant difference. What this means is we haven't given poor old Dad enough chances to demonstrate whether he has a Y chromosome. Put another way, this simply means that looking at data from only 3 children is not enough data to make a firm, statistically supported conclusion. So, in this case, 3 daughters and 0 sons is not statistically significantly different from the expected ratio of 1.5 daughters to 1.5 sons. This raises a great question for you to try to solve to apply the knowledge you just learned. How many children of only one sex would a family have to reach the level of statistical significance that would prove that a father had no Y chromosome, which is why he was never able to produce any sons? Thanks for watching, and please be sure to be in touch if you have any questions.